Okay, here is an Alex problem that deals with first order kinetics, and it gives us a rate constant right here. It is using this chemistry that we have right up here, okay, that we have Cl2O5 that is then going to react and give us this chlorine, Cl2, and this oxygen as well. And so it gives us the Cl2O5 at this concentration of 0.860 molar, and then wants us to calculate the concentration of Cl2O5 in this vessel 430 seconds later. So I got 3 sig figs right there, but then it says in our answer, let's round that to 2 sig figs. Alright, so again, what I do is I just have to write these rate laws, these integrated rate laws down so that I know those. So the differential rate is going to be rate is going to equal to some constant, k, that's going to be raised to a to the first power. The integrated law is going to be the natural log of the concentration of A at a given time point is going to be equal to the natural log of A at the original concentration minus K, some constant, times T. Okay, so that is my first order integrated rate law that allows me to look at concentrations at given times. That's when we would use these types of things. And so now that I have that, I can look and see, well, I'm given a concentration, initial concentration, I'm actually given a K and I'm given a T. The T is 430 and the K is right here that are in units of per second. Okay, so let's go ahead and just do this math. This is now just a plug and play. We do have to deal with natural logs, but you guys can do that. So the natural log of A at a given time is going to be equal to the natural log of the initial concentration, which is going to be 0.860 molar, minus K, which is 0.00303 per second, times the time, which is going to be 430 seconds. Okay, it's a multiplication. So when we go ahead and put these into our calculator, I get that the natural log is going to be minus 0.1508, and that is going to be minus, when I do this math, is going to be minus 1.3029. Okay, so now I'm going to go ahead and say that the natural log of A at time point 430, it's what we're interested in, is going to equal minus 1.4537. That's what I get when I do this little bit of math right here. Okay, so now how do I solve? And some of us will have to remember this. Okay, what I can do is I can then say that the A raised, or the concentration of A at 430 seconds is going to equal E raised to the minus 1.4537. This is how we get rid of that natural log. We raise E to whatever's on the right hand side of the equation, and so the concentration of A at time point 430 is going to equal, in this case, when I do that, that's going to be 0.233. That's molarity. And so we want to keep this in units of molarity. The answer is going to ask for that. And so the answer to 2 sig figs then is going to be equal to 0.23 molar. And that's what I would put into my Alex. Okay, so again, how do I do that? I just have to write down these rate laws. I will give them to you on a test. You don't have to memorize this, but you do have to know what is going to be zero order, what's going to be first order, and what's going to be your second order integrated rate law, and you're going to have to know how to deal with the natural logarithms in there as well. But these are definitely doable, often just plug and play.